Right, well, good evening, everyone, and welcome to another one of our online meetings. And I'm very pleased to see that we have also been joined tonight by a number of guests from outside of our membership, including members from the North Essex, the East Essex, Castle Point, Loughton, and Thurrock Astronomical Societies. It's a pleasure to have you all with us, and I hope you enjoy this rather special presentation this evening. Our speaker this evening is Professor Dame Jocelyn Bell Burnell, who is most famous for her accidental discovery of pulsars in 1967, along with her PhD supervisor, Anthony Hewish, whilst at Cambridge University. Before making her discovery, she assisted in the building of the radio telescopes that she used in the fields outside Cambridge. At first, the regular repeating radio signal was a great mystery and thought possibly of human origin. However, it became clear that this radio signal probably originated in outer space. Jocelyn then discovered another similar signal, and it became evident that they were probably from neutron stars rather than the little green men that she'd written on the chart recorder graph. When the Nobel Prize for Physics was awarded to Martin Ryle, the leader of the radio astronomy group at Cambridge, and Anthony Hewish in 1974, it was the first time the award had been given to astrophysics, which was then a new branch of science. And soon, other astrophysicists followed in their footsteps. Jocelyn was born in Belfast and brought up in nearby Lurgan and attended Lurgan College, which at the time only allowed girls to study domestic science. Jocelyn's parents complained, and she was able to switch from cross-stitching to physics. She became interested in astronomy when her father, an architect, was commissioned by Eric Lindsay, the director of the nearby Armagh Observatory, to design a planetarium. Patrick Moore was its first director. Lurgan is about 50 miles from Strabane, the childhood home of Annie Maunder, whose life story was related to us a few weeks ago by Louise Devoy. Unlike Annie, who failed in an attempt to be elected as a Fellow of the Royal Astronomical Society in 1892, Jocelyn has gone one better and was actually president of that society between 2002 and 2004. She was also been the president of the Institute of Physics from October 2008 until October 2010. In 2007, Jocelyn was made a Dame Commander of the British Empire. Like her fellow Irish-born scientist, Dame Kathleen Lonsdale, she was very active in the Quakers. In 2018, Jocelyn was awarded the Special Breakthrough Prize in Fundamental Physics, and she decided to give the whole of the £2.3 million prize money to help female, minority, and refugee students in becoming physics researchers. The resulting bursary scheme is known as the Bell Burnell Graduate Scholarship Fund. After taking a PhD on quasars, she has worked at the University of Southampton, University College London, the Royal Observatory in Edinburgh, and the Open University. She is currently a visiting professor of astrophysics at Oxford University. I'm therefore very pleased to introduce Jocelyn this evening, who will be speaking on the subject of bursts, bangs, and things that go bump in the night, which is transient astronomy.
Let's go then, Les.
Okay. Slide 2 then, yes? There we go.
Right, and I'll move mine to slide 2, so I'm looking at the same thing. So this picture shows a famous photograph taken by the Hubble Space Telescope. It's the deepest photograph ever taken. They exposed the camera for 143 hours, and it's a tiny, tiny area, what a tennis ball would cover at 100 meters. And it's interesting for the astrophysicists. First of all, there is some black in between all the other things. Almost everything in the frame is a galaxy. There's one star just left of center. You can see it's a star by the cross shape through it. And some of these galaxies are some of the very early galaxies. We're looking back about 12 million light years. But to get that, I say again, you had to expose for 143 hours, a long time. Could I have the next slide, Les?
Yep.
Slide 3.
Yes, we're there.
Good. Okay. So that's a very small area where we drilled down very deep. It does seem to be a fairly typical area, which is good. And it's given fantastic results. But because of the very long stare, you miss anything that changes, that moves, that flares, that dies during that stare, because that change just gets averaged out. And so you're missing quite a lot of events, things happening. And it's these kinds of things that the attention is turning to now. Could I have the fourth slide, Les?
Okay.
So what we need to do is the equivalent of moving from still photographs to movies, where you have a sequence of exposures taken quite rapidly, and you can see things that move or things that change their brightness. And the fifth slide, please.
Okay.
So this is a whole new branch of astrophysics that's really beginning to boom now, and with some very big facilities coming on. It's particularly impacting the optical astronomy community. Pulsar radio astronomers are used to things that change with time. X-ray and gamma ray astronomers have also been used to things that change with time. But the optical and infrared and ultraviolet astronomers, less so. And the next slide, please.
Okay.
So there's this new field now running primarily in the optical called optical transient monitoring. And initially, some little old telescopes got taken over for this. So there's a Schmidt telescope owned by Uppsala, actually in Australia. They've used that to do some rapid monitoring. There's the one on Palomar that I'll talk more about. And there was a new one as well called Atlas. And could we have the next slide, Les?
Okay. There we go.
Thank you. So this shows two photographs of the same patch of sky. And in the middle of the field is a star that's changed brightness. It's got a nice red ring round it in the right-hand frame. This was done by visual inspection of photographs. These days, you'd use computers rather more. And then you have to decide how long you stay on one patch before you move to another, and how frequently you come back to that first patch. All that's called the cadence. And if you see a change, you also have to have a mechanism for announcing the change rapidly so that other astronomers can follow up with other telescopes and at other wavelengths. Thank you. And the eighth slide, please.
Okay.
So this is back to Mount Palomar and the Schmidt telescope there. It's now known as the Zwicky Transient Facility. It's been running now for about 2.5 years. Returns every 3 days to the same patch of sky. And it's finding something like 10,000 things that rapidly increase their brightness. Explosive transients every year. It's also generating 4 terabytes of data per night, and they're having to use machine learning to help analyze the data. And they'll soon have several petabytes of data. It's a new CCD camera on an old Schmidt telescope. It's good because it's got a wide field of view. They're using 3 optical bands, and they reckon they can get down to 20.5 magnitude. And can we go to the next slide, please?
Okay.
So this Zwicky Transient Facility, it's generating 1 million alerts per night. It sees changes in 1 million things every night. Lots of supernovae, the big exploding stars, asteroids which move. Then there are things called tidal disruption events, which I'll talk about. They're finding one of those every month. And not only are they studying or counting the number of stars that explode as supernovae, but they're beginning to get information on how supernovae interact with their environments. And to the next slide, please.
Okay.
Supernovae have become quite important because they're being used by cosmologists. They're trying better to get the dark energy equation of state, and they're also trying to get the expansion rate of the universe. You may be aware of efforts to measure the Hubble constant. This is one of them. And at the moment, there are 2 or 3 methods of measuring the Hubble constant. Each has got improved accuracy, and they are now inconsistent with each other. So we're in an interesting situation. And the next slide, please.
Okay.
So the Zwicky Transient Facility works with other telescopes, other wavelengths, and other things that come in from the cosmos, like neutrinos and gamma rays and gravitational waves. And it's identifying the optical counterparts of all of those. This is all very new, so it's getting very, very interesting and very exciting. And the next slide, please, Les.
Okay.
So now we're on to microlensing, if I'm keeping up with you right, Les.
Yes, indeed.
So microlensing, what is this? This is one of the things that the Zwicky Transient Facility has got very strong on. It depends on Einstein's theories. It depends on a massive body bending light rays. So in the diagram, we have the Earth on the left and the source, a star that you're trying to observe, on the extreme right. And all the stars are gradually moving relative to each other. And it so happens that another star comes between you and the star you're wanting to observe. And the effect of this intruder star's gravity is to bend light rays. And light rays that should have headed off to the top left of the diagram from the source star now get bent and come to the Earth. And so do rays that should have headed off to the bottom left. They get bent and come to the Earth. So temporarily, the Earth gets a lot more light from the source star. It appears to have flared. And by studying the flare, you can actually get quite a bit of information about that intruder star in the middle. So if we move to the next slide, which should be number 14.
Yes.
Okay, up top is a yellow dot. That's the star you're wanting to observe. The red thing is the intruder star, which is passing by. And the little sketch graph at the bottom shows the way the yellow star brightens. And if we read the frames from left to right, the extreme left one is just the simple case where a star intrudes. Next one along, the intruding star has a planet, which is a little gold-colored dot. That planet can itself also focus some light rays. And so you see the main brightness increase due to the star, the red star, but then you see a little blip on the right-hand edge of it, which is due to its planet. So you can tell whether or how many planets that intruder star has. Sometimes the planet is following quite a long way behind and the 2 blips are detached. That's in the widest part of the panel. And that's all explicable. But what we didn't expect was to find little blips due to planets, as in the right-hand panel, with no sign of a parent star whatsoever. Not now, not later, not never. There ain't a parent star. This is an isolated, a lonely, poor thing planet. These things have been christened either orphan planets or rogue planets, I think, depending on your psychology, whether you're optimistic or pessimistic or what. They're all called free floating planets, and they don't seem to have a parent star. And they now know about 15 of these. And there are probably many, many more. Once you find something, once you know what to look for, you often find more. Could we go to the next slide, please, Les?
Yes.
So far I've been talking about what optical astronomers do. This slide reminds us that there is a very big range of radiations like light, but our eyes don't pick them up. Our eyes only pick up that little rainbow in the middle. As somebody once said, we are electromagnetically challenged. And how? Because we don't see ultraviolet out the violet end of the spectrum. We don't see X-rays going further out. We don't see gamma rays going further out to the right. And going out to the left of that little spectrum, we don't see infrared, we don't see millimeter, we don't see radio. All these wavelengths are now getting involved in this business of time variable sources, transient things, things that go bump in the night, so to speak. Can we move to the next slide, please, Les?
Yes.
So I'm going to start at the extreme right of that last diagram and talk about transient gamma ray events. There's a lovely story about their discovery. Way back in the 1960s, the USA signed a test ban treaty with the Soviets that there would be no nuclear tests in the Earth's atmosphere. Being trusting folk, the USA decided they really ought to monitor to check that the USSR was not quietly doing tests. The tests would have given bursts of gamma rays, so the US put up several satellites to look for bursts of gamma rays. And they aimed to have 2 or 3 up at a time so as they could get a fix on where the gamma rays were coming from. These were known as the Vela satellites. Can we go to the next slide, please?
Okay.
So starting in 1967, they started finding bursts of gamma rays. Ho ho, these wicked Russians. But then the scientists realized that these gamma ray bursts were not coming up from the Earth's atmosphere, they were coming down from the sky. Something way beyond the Earth and the solar system and the Russians was producing bursts of gamma rays. But of course, this was military, highly secretive stuff, and the scientists couldn't get clearance to announce these things for about 6 years. 1973 was the first the rest of the world knew about these gamma ray bursts. The diagram shows you one gamma ray burst in particular. It's a much later one from 1997. 1997, December the 14th. And you can see that it's all fairly quiet. You can see the kind of noise level. And then suddenly there's this very strong burst where the signal goes up hugely. And then after 20 seconds, it drops away again and it all goes quiet. And that's very typical of a ray burst. Could we have the next slide, please?
Okay.
So the big question was, everybody started looking for these and finding them. Talk about knowing what to look for and then seeing it. We're currently seeing about 1 a day. And while it's on, the burst is the brightest thing in the gamma ray sky. The oval on the right-hand half of this diagram with all the coloured dots is a map of where the first 2,700 gamma ray bursts had come from. It's in galactic coordinates, so the Milky Way would run along horizontally between where it says plus 180 and minus 180. And they plotted this map to try to see if there was any clustering to the Milky Way. And actually the spattering is absolutely even. There's no clustering to anything. So it doesn't look as if the Milky Way is important. Indeed, if you think about it a bit, this kind of spattering either means that the objects are very, very close, much closer than most of the galaxy, or very, very distant. Those are the two ways you would get this spattering without any sign of the Milky Way. And the debate was on to try and understand whether these were very, very close or very, very distant. The energetic consequences of them being very, very distant was quite severe. So the very near brigade had quite a strong following. Can we go to the next slide, please?
Okay.
As we observed these gamma ray bursts, we discovered that they actually were of one of two kinds, either what we call short duration or long duration. Short duration is less than 2 seconds. Long duration might be up to 100 seconds, but longer than 2. The next slide, please. The long bursts we now think are due to supernovae or supernovae called hypernovae. A hypernova is where a high mass star collapses to make maybe a neutron star like a pulsar, or a quark star, or a black hole. And as part of the collapse process, you can get a very narrow jet of X-rays. And if this jet is pointed at your satellite, then it will see a gamma ray burst. Short gamma ray bursts took a lot longer to explain. We go to the next slide, please.
Okay.
In terms of discovering where they came from, this was the breakthrough observation. There are optical observations, 2 observations of the same piece of sky. The earlier one on the left, the later one on the right. They're done with different telescopes, so there's a different amount of sort of speckling on the photographs. But in 1994, where the arrow's pointing, there's actually nothing very much. But in 1999, something has appeared where the arrow is pointing. The ring in that right-hand photograph shows the area that the gamma ray astronomers said the source should be in, and it's the only thing that's changed significantly within that circle. Again, there must be a very narrow focused beam, and that thing turned out to be an external galaxy at quite a distance, quite a healthy redshift. So some of these gamma ray bursts are coming a long, long way. And we now reckon that there'll be a few from each galaxy per million years. Go to the next slide, please.
Okay.
So leaving gamma ray bursts at that point and going on to a totally different phenomenon that's really only very recently been seen, although it's been thought about for a while, called a tidal disruption event. And this is caused by a black hole. We change slide again, please. So the picture shows the progress of a star that's coming on a track that brings it too close to a black hole. Where it starts up in the top left, it's okay. It's not really seriously affected by the black hole. But as you come down to the tip of the arrow, there are tidal effects that stretch the star out into the cigar shape and begin to pull it towards the black hole. And then the cigar breaks up into lots and lots of little blobs, little bits, and they fall in one after another. And there's generally a little flare around about each one just as they go over the edge. Whether it's a gamma ray flare, an X-ray flare, a radio flare, or what, optical flare, most we've seen so far are in the optical, but that might be because we're not good enough at recognizing them in other wavelengths. But they've now seen something like 60 of these tidal disruption events. And again, the next slide, please.
Okay.
Thank you. So now I'm going to talk about some recent events in radio astronomy. To this spectrum, we're now going to the extreme left of this. It's the same kind of radiation as our eyes see as light. It's just much, much longer wavelength where our eyes don't operate. And you have to use radio telescopes. A little bit of physics. Probably all seen a rainbow, and maybe seen, as in this picture, a beam of light being split by a prism. It's exactly the same as sunlight being split with a raindrop. You get a little rainbow. And this happens because the white light that arrives on the raindrop is split by the raindrop into the different colors, and the different colors travel at different speeds and get bent different amounts. And so the white light then gets spread out into its rainbow, its spectrum. Something similar happens with radio waves, only we're not using beams of light and prisms. Can I go to the next slide, please?
Okay.
I'm going to try playing this audio. I have no idea whether it works. Les, you might tell me if it's not working.
Yeah, I'll do it from my end if you like.
Yeah, okay, there'll be a lot of crackle, and then you'll hear a descending note.
No, you might want to try it from your end.
I'll try it from my end, you never know.
There we go.
Whoops. So that kind of noise, that is what's called a whistler. And if you're interested in radio, you will have heard whistlers. A whistler is caused by a lightning stroke on the far side of the Earth. And the lightning stroke produces a sharp pulse of radio waves, which then travel round to our side of the Earth, looping round, following the Earth's magnetic field. And as it loops around, it goes past some electrons, some free electrons. And the free electrons slow up the lower frequency waves. The higher frequency waves arrive first, followed by the lower frequencies. And so you get this descending note. This happens in the Earth's ionosphere, Earth's magnetosphere, for lightning waves, for radio waves from lightning strokes. It also happens in space for pulsar signals, for example. There are free electrons in space, and even though the pulsar goes and produces a whole range of frequencies all at once, the radio astronomer picks up the higher frequency first, followed pretty rapidly by the lower frequencies. Can we move to the next slide, please?
Okay.
So this is a picture of it's a very small star, about 10 miles across. And I do just mean 10 miles, not 10 to the power of something. It's spinning very accurate, very fast. Its spin axis in this diagram is straight up and down. And it's got a very strong magnetic field, and magnetic north is not at true spin geographical north. And somehow, for reasons we don't fully understand, a radio beam or two radio beams come out of these two funnels at the magnetic poles and sweep around as the star spins. It's a bit like a lighthouse sweeping a beam around the horizon. If you're in the path of the light beam, you see it. If you're standing below the lighthouse, for instance, you don't see it because it doesn't shine in your eyes. Well, some pulsars shine their radio beam on Earth. Probably 99% of them don't. And can we go to the next slide, please?
Okay.
So pulsar astronomers have to check that this pulse that they pick up has come from way out in space, long, long away, far, far away, and isn't just a lightning stroke on the other side of the Earth. So what they do is they check that the radio frequencies have got spread out. The high frequencies arrive before the low frequencies. We've got an example here of a couple of pulsars. The actual pulse you can see in the top of the two frames. The first one is quite broad and noisy. The second one is very strong, narrow and sharp. And underneath you see this graph of frequency against time. And you see the line curving down, starting under the pulse and then curving down and down and down. These curved lines show that the pulse has come from something way out in the galaxy and not just from the neighborhood of the radio telescope. And pulsar astronomers always make these kinds of plots and always check on the distance that their pulse has come. Could we have the next slide, please?
Okay.
So here in the black part of the picture, you can see the pulse. It's wonderfully strong, wonderfully sharp and short, and stands out like a sore thumb. You couldn't miss it. And then behind it on the yellowy graph is this curving line down, showing that it's not locally produced, it's come considerable distance. How slowly that line falls down depends on the distance. The more distant it is, the longer it takes to fall down. And when they looked at this line on the yellow plot, they found that it was falling very, very, very slowly, quite unlike any pulsar known up till then. Furthermore, they never got another pulse from this direction, from this pulsar or whatever it was. And it turned out that to make this signal so spread out in frequency, you needed far more electrons around than are available in our galaxy. So it has to be from beyond the galaxy. The snag is once you reach the edge of the galaxy, electrons are very few and far between until you get to the next galaxy, if there is one. And so this very sharp spike had to be extragalactic and not repeating. We've now found hundreds of these, and in very few cases is there anything to be seen by optical telescopes or infrared or X-rays. And where there is an optical signal, it's a pretty ordinary kind of galaxy. They've managed to position 4 or 5 of them now, and they're all in the outskirts of massive galaxies. Well, that's some information, but it's not a big help, to be honest. So, yeah, we've now seen over 3,000. They're from way outside the galaxy, and a few have been seen to repeat. I'm going to crave a bit of an indulgence and tell you a story about something that nearly happened. The Australian radio astronomers at the Parkes Observatory were seeing other kinds of bursts as well as these fast radio bursts, as we now come to call them. And these other bursts look slightly different, and they came from all over the sky, any old way, and didn't seem to repeat, and they could not make sense of them. Until a graduate student decided to do a plot of when these bursts occurred against local time. And this plot showed that there was an excess of bursts between 12 noon and 1 p.m. What do you do between 12 noon and 1 p.m.? You have lunch. There's a canteen, self-service canteen on site with a microwave oven in it. But they knew that the microwave oven was leak tight because they had tested it and tested it and tested it. And then, this is where this message applies to you as well. And then they thought, I wonder if somebody opens the door of the microwave while it's still on. Does it stop quickly? And the answer is it doesn't stop quickly. So next time you're using a microwave oven, please use the stop button. Don't stop the microwave by opening the door because you get a short blast of microwaves in your chest. And that's probably not too good for one. So having eliminated this hazardous source of bursts. They were then able to get down and really study the ones that they were picking up. And it is the Australians who've identified the origin of most of the bursts. So some of them are from the outskirts of massive galaxies. Aha. Could we go to the next slide, please?
Okay.
There are some new telescopes coming online, and they're going to add some interesting data. Next slide, please.
Okay. Yep.
Good, thank you. So this is two distant photographs of Canada's new radio telescope. It's in British Columbia. It's in a valley amongst the Rockies, which screens out a lot of radio waves. You might be able to see in the right-hand image there, you're looking at 4 cylindrical troughs, which are almost end on to us. You're looking along the length of them. It's a fairly simple kind of radio telescope. It works beautifully at detecting fast radio bursts. It's not been very good at positioning the sources of the bursts, but it's useful because it's seeing a number and it's showing that they they radiate at lower radio frequencies than any other telescope has been observing them. Could we go to the next slide, please?
Okay.
So just to check, this is slide 35?
Correct.
Good, thank you. So a big new optical telescope that's coming on that's very, very exciting. It's been known until very recently as the Large Synoptic Survey Telescope, but the observatory it's in is being named after a woman astronomer, the first time a telescope's named after a woman, the Vera C. Rubin Observatory. It's in Chile, in the north of Chile. It's going to start operating in a couple of years' time. It's got a mirror that's 8.4 meters. You can perhaps see on the mid-level gallery on the left in white a little person to give you scale. And there's another one on the lower level at the right-hand end of the gallery. It's huge. Its camera will have 1 billion pixels, and the camera itself is as large as a small car. Sorry. And can we go to the next slide, please?
Okay.
It's going to scan the sky, the entire sky visible from Chile every few nights. It's going to end up with a catalogue of 6 million solar system bodies. That's going to include a lot of very small lumps in the solar system and 37 billion stars and galaxies. But it's there to look for things that have changed brightness, changed position. And it's reckoned it's going to find 10 million of them every night. 10 million per night. There's no way human beings can keep up with that. The analysis has all got to be done by computers. So we're into machine learning. And it's going to be quite tricky to program the machine to identify things that you didn't know existed. It's fine for the kinds of things you know about, but not for totally undreamt of things. So that's going to be very interesting, watching all that. The next slide, please.
Okay.
In Australia, they're going to be building part of the square kilometre array, and they have a precursor. It's called ASCAP, and this picture is our ASCAP, the Australian square kilometre array precursor. The other half of the square kilometre array is being in South Africa, and both the South African ones and the Australian ones are making the detection of transient events some of their key projects. The South African precursor is an enlargement of an array they previously had called the Karoo Array Telescope, or CAT. And so they have called their precursor Meerkat, because meer means more in Dutch. So Meerkat is the South African equivalent of ASCAP. And Meerkat is also doing transients. But very cleverly, they have put in amongst the radio dishes a small optical telescope which covers the same field of view as the radio telescopes and is slaved to point the same way as the radio telescopes are pointing. So if the radio telescopes pick up a burst, then the optical telescope can say, oh, we saw that too, or we didn't see that too. And this little optical telescope is called meer licht, more light in Dutch. And can we go to the last lot of slides, and I'll try and speed up.
No, you're okay. We're on the next one.
So we're talking about the final kind of radiation called gravitational radiation, which is not on that spectrum that I was showing you at all. It's a whole new spectrum. We've recently had a whole new spectrum open up. Incredibly exciting. Could we have the next slide, please, Les?
Okay.
So the animation is from Wikipedia. It's an exaggerated version of the waves that there would be in space-time if you had a pair of stars orbiting each other, probably a pair of neutron stars. There are many things that can produce these ripples in space-time, and they travel out at the speed of light. Can we go to the next slide?
Okay.
Actually, I think I'll skip this one. Can we go to number 41?
41. Sure.
Now, as that pair of stars that you were watching in the previous slide orbit each other, they give out this gravitational radiation, and that takes energy away, which makes the two stars move closer together, which means they go round faster, and there's stronger gravitational radiation, which means they have to move closer together where there's stronger gravitational radiation. They move closer together and radiate even more strongly. And finally, they bang into each other, crash. And that gives the waveform theoretical waveform that you see in this picture. So it's a bit boring to begin with, but then the frequency gets faster and the amplitude gets larger. And finally, the two things merge. We go on to the next slide, please.
Okay.
It's been a long haul getting the gravitational wave detectors working at the right sensitivity because the waves are actually very, very weak. But in September 2015, they got their first detection. This is the signal. They used two separate detectors to give themselves confidence. One gives the orange line and the other gives the blue line. And for about the first, up to about the 0.3 point, it's just rubbish. But then you begin to see the two things are actually syncing very nicely. And it's a noisy version of that theoretical waveform that I've just showed you. And this turned out to be two black holes, each weighing 30 times the mass of the sun, merging. And they were at a distance of about 1 billion light years. We didn't know there were black holes in this mass range, but LIGO, the Gravitational Wave Observatory, is finding a lot of them now, and relatively few neutron stars, which is what they were meant to be finding. Can we go to the next slide, please?
Okay.
So we talked about gamma ray bursts, and I said I'd tell you later what gives the short gamma ray bursts. In the top part of the picture, we have two neutron stars orbiting each other. As they emit gravitational radiation, they begin to move closer together and spiral inwards and finally merge. And from the merger, we get this short and relatively weak gamma ray burst. And that's because of the gamma ray burst. That's how they managed to identify the first detection of gravitational waves. So if we move to the last slide, transient astronomy is certainly coming of age. There's lots of exciting stuff beginning to happen. There's going to be more and more happening. And it's an area I'm watching with great interest because there's lots of punch and lots of drama. Thank you very much for your interest and your attention. And thank you, Les, for the help with the slides.
Oh, you're very welcome. Okay. So, Les, would you like to comment, please?
Yeah, right. Okay. Well, Jocelyn, thank you very much for that very informative and interesting talk on an aspect of astronomy of the future, basically. It's taken us to the next level, further out and further afield. I'm sure that I can speak for everyone here that enjoyed that very much. But Les, if I can ask you to do the usual and unmute everybody, I'd like to ask everybody here to show their appreciation in the traditional way, please.
Right. Sorry, I had to mute everybody again just because of the
Sure.
background noise. So thank you very much, Professor Bell. As you can imagine, we have quite a few questions that have come through on the chat. So if I may just check with you in terms of, do you have a few minutes that we can go through some of the questions?
Yes, I'm fine. It's how long you can hold out.
No, I think we're absolutely fine here. So, and I'm just going to check to see. No, we haven't had any other questions from the other route. So let's just go through some of the ones that have come through. I don't think there were too many duplications, but we do have some. So depending on how we get on, here we go. So a question from Liz. I think it was sort of fairly early on. You mentioned where are the sort of 1 million alerts sent and who looks at them? And I think that sort of segued into a point you made towards the end about all of the data and the millions of sort of basically observations that are becoming in per night. How's that going to be handled?
Yeah. The difficult thing is not so much the computing, it's the transfer of that amount of data. And so it's got to be kept pretty local. I don't know a lot about how they're planning it, though. I don't know that I can add to that. But you can't ship large quantities of data around very easily. You could probably build enough processors to analyze it, as long as you can get the data to the processors.
Okay. We have another question here. To get an optical result on neutrinos, etc., I'm not sure that's possible, but to get an optical result on neutrinos, what do these look like? How does it work? I think, again, that was referring to one of your sort of beginning slides.
Yeah. Neutrinos, I'm hazy, I must admit. I don't think I can answer that without doing some homework.
Okay. I guess they're very difficult to detect anyway, so billions of them are passing through us, aren't they?
Yes.
So,
Yes.
okay. Another question here. You mentioned the lonely planets or the rogue planets. How do you think they've actually got into that situation, and where does the light come to illuminate them enough to be seen?
They are not directly seen. The effect of their gravity is seen as they pass across in front of you. So that's the only way of detecting them, is by the way they focus the light from a distant star temporarily as they pass across in front of it. How they came to be? Well, they must have been formed in a system a bit like our solar system somewhere. Maybe that solar system got broken up by a passing star or something, and the planets were cast loose. Probably something like that.
Okay. Could be that the formation of our solar system may have created, and a passing star may have created a rogue planet that's somewhere else, I guess.
Yes. Yeah.
We have a question on the tidal disrupted event. So over what sort of period of time does that happen?
Some of it's just on a matter of days, but some of the radiation can go on for a year or so. Well, several years. Depends whether we're talking about a star-sized black hole or a massive black hole in the center of the galaxy.
Okay. Is there a particular polarization for the radio waves from a pulsar?
The radio waves are polarized, but the plane of polarization swings as the pulse goes past. So you're best not using a polarized radio telescope, because the position angle, as they call it, does change as the pulse goes through.
Okay. And sort of connected with that, but it's relating, why do pulsars have a magnetic field at an angle to the spin?
We don't know. That picture is the only way we can explain what we're seeing. But why? I don't know. And incidentally, the magnetic field has to be huge, really, really big, millions of Gauss. So there's a lot unknown about neutron stars and pulsars, even now.
And on that, what's the difference between a pulsar and a neutron star?
There are neutron stars that are not pulsars, but we believe all pulsars are neutron stars. So, for instance, X-ray astronomers quite often see a neutron star twinned with an ordinary star in a binary system. That's a classical way of getting X-ray emission. Whereas a pulsar will be normally isolated. There won't be another star around.
Okay. And you mentioned the electromagnetic spectrum. Have there been transient phenomena in the infrared?
There must be, but there's not a lot of work done on that, I have to say. I don't know a lot. There must be transients that you observe in the infrared, but I'm not sure that anybody's in infrared is doing much of that, to be honest.
Okay, and question about the new optical scope in Chile. If the question is, as a byproduct of its capabilities, could it be picking up wandering debris, I guess asteroids and the like, which could be potentially hazardous to Earth?
Yes, undoubtedly, assuming that they emit enough light for it to pick up. But yes, indeed. That's all part of the sort of transient area of research. Yes.
Yeah.
Indeed, it's the way some US astronomers have got funding for their transient research. We'll pick up killer asteroids coming to hit Earth.
Wow. Well, I guess any way that's going to attract funding is probably beneficial. Yeah. You touched on the need to sort of manipulate huge amounts of data and machine learning. To what extent do you think artificial intelligence, I guess, as a sort of a machine learning sort of approach, will play a role in analysing the vast amount of data?
It's got to play a big, big role, because there's no way humans can handle that amount of data. The one thing that worries me is how you program a machine to look for something you didn't know existed. That's an extension of my work on pulsars. If we had automated the analysis of data, if we could have, we would not have programmed it to look for pulsars because we didn't know they existed. This has got the same kind of issue, only this time in the optical, not the radio.
I guess it's looking for the anomalies and recognizing that there's something behind, there's some sort of cause and effect there.
Yes, and that it's not just an instrumental glitch as well.
Yeah.
Yeah.
Okay. Just one or two more, if we may.
Yes.
Have gravitational waves disproved the modified Newtonian dynamics or Mond theory?
I'm not fully up to speed on this. If they haven't, the pulsar astronomers are also. There's a binary pulsar, a binary system where both objects are pulsars, and that is putting very, very severe constraints on most theories of gravity. So Mond is one of the theories of gravity that's being constrained by the double pulsar.
Mm-hmm.
So it's certainly happening there. I don't know where else might be tackling it, for sure.
Mm. Okay. Couple of related questions in terms of the our galactic center and the black hole at Sagittarius A star. Is this unusual, where black holes have galaxies around them, and do most galaxies have black holes, or do most not, or black holes in other sort of isolated places in space?
It seems that there are regularly black holes at the centers of galaxies. Ours is a little feebler, tamer than typical, I think it's fair to say. And some, of course, like in the centers of quasars, are really very active. But yes, it seems to be very much the norm that there's a massive black hole at the center of a galaxy.
Mm.
What I don't know is, do dwarf galaxies have black holes? I just don't know. There must be. I don't know if there's information on that yet.
Okay. Final couple of questions, and one sort of fairly general, and I hope you won't mind answering it. What, given your sort of history and your research over the years, what's a typical day for you now?
Well, I'm supposed to be retired. Supposed to be. Apart from the sort of COVID and lockdown and all that kind of thing, if we were out of lockdown, shall we say, and universities were functioning normally, I have a visiting academic post in Oxford, a desk, a filing cabinet, desk piled high with paper, like many desks are.
Mm.
And there's a group of probably about a dozen people doing research on areas close to my interests. I'm no longer research active myself, but I am trying to keep up with the field because I'm doing quite a lot of talks. And the questions following this talk have been particularly on the ball. But you need to know your stuff. You need to keep up with what's happening.
Indeed.
Being in Oxford is a brilliant way to do it.
Excellent. I think we really benefited from that. So, final question in our chat, and it's prefaced with great honour, many thanks for this talk, and I think that's echoed by everybody on the call participating. What are the main questions that you feel would need to be answered, in this field over the next few years?
I think we haven't yet discovered all the time variable phenomena that there are to be discovered. I'm fairly clear about that. I don't know whether the new stuff comes from, so to speak. Obviously, when the telescope in Chile is functioning, it'll deliver a lot of stuff. Until then, it's probably things like this Vicky transient facility that finds stuff. We are finding a lot of highly energetic, time variable things, which we haven't yet been able to properly understand. There's quite a bit going on already. If people want to learn a bit more, Google cow, C-O-W. There's an object with a number, you know, da 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 da, C-O-W. So it's known as the cow. Surprise, surprise. There are a lot of curious objects like that. Objects with curious behavior like that we are finding, and we don't know what they are. And just in the last couple of years, a lot of people have suddenly realized how exciting this time domain stuff is. And a lot of people are now doing work in it. So there's a lot of activity building up in part for the Rubin telescope in Chile, but it was going to happen anyway, I think. And then there's all the gravitational wave stuff, which is still very new. And I think there's a lot more exciting stuff to come out of that. So for my money, I would watch the gravitational wave observations and this time domain for transient phenomena. I think there's still many, many surprises, maybe some big surprises to come. So lots of fun to look forward to.
Indeed. Stay tuned.
Yes.
And if I may be permitted just to ask one question myself, and it's really on the whole sort of research piece, but what you might use or coin the phrase of the inclusion and diversity, and encouraging more diverse sort of background of people into research and so on. What do you feel are the challenges still remaining in that, especially given your donating your prize to create that sort of wonderful legacy for underrepresented parties?
If you look around at typical astrophysics department, it's still predominantly white males. The fraction of women is growing. It's better in astrophysics than in many bits of physics, but that's not saying a lot. So the diversity is getting better. The money that I donated the first awards have just been made of that. And the first 4 recipients are 4 young women. 2 of them are from countries overseas who've come to Britain in the last year or 2. One is from really rather poor, short of money background, who came to university, I think with a D overall, she arrived with, and she's going to go ahead and do a PhD. So there are some wonderful stories, even amongst this first cohort, and I think there'll be lots of other interesting stories in subsequent years. So the first 4 recipients start their PhDs in October-ish, depending on how universities are going to function.
Well, fantastic. What a wonderful endowment. So to benefit science as a whole, but society in general in those underrepresented areas.
Well, we hope so. We'll see.
Fantastic. Jocelyn, that's all of the questions that we've got in the chat. So I'm going to hand back to Les for some concluding remarks. Thank you very much.
Right, yes, thanks very much, Reza. And again, thanks very much to yourself, Jocelyn, for the talk this evening. Right, yeah, everybody, I'm hoping that likely you enjoyed that the presentation by Jocelyn this evening. Just a few notes to point out for following meetings we have. Our next online meeting is going to be on Wednesday, the 2nd of September. It's going to be slightly earlier than usual. It's going to be at 6:45 for 7, because this presentation is going to be coming to us from Greece. It's going to be given to us by Dr. Anastasia Kokori, who I see has joined us for this evening's presentation. She's the Public Engagement Officer at the University College London Centre for Space Exochemistry Data, and her talk is going to be on the ExoClock project for the aerial mission. So that's Wednesday the 2nd of September. And then the next one will be Wednesday the 16th of September, back to our normal time of 7:45. And this one is a regular and popular speaker to our society, Mr. Paul Money, who some of you may also know as the reviews editor of the BBC Sky at Night magazine. This talk is going to be entitled The Vikings at Barsoom Part 2, Search for Life, which is about the early missions to Mars. This talk is the second of two. Some of you may remember that the first The Vikings at Barsoom Part 1 was given last year when we were still holding in-person meetings at the community centre. So they're the two up-and-coming ones for September. Obviously, if you want to take part again, you should have the details from Les, but if not, contact him. On that point, if any members would like to give a short talk or presentation online, can they please contact Magda or Peter? Obviously, there's other things to do whilst on lockdown. And if I can refer you to our website, the Havering Astronomical Society website, www.havastro.co.uk, where you'll find such items as Peter's Objects of the Month, his deep star objects. Then there's also Martin's monthly challenge, and other links to other sites as whatever. And also, if you can have a look at the Society's Facebook page, where members and other people put on items of interest on there. So that's some other things to keep you occupied in the meantime. So I'd just like to end that on to say by thanking you all for joining us virtually tonight. Hope you keep safe and well, and hope to see you again in the future. So that's good night from me.